So what went wrong? It was initially set to be launched on the 12th of January 2003 and had a totally different target. But the Ariane 5 rocket had a major failure a few months previously with another mission, meaning all launches were grounded until they could determine and fix the problem. Once in space, the Rosetta spacecraft had an eventful 7-year journey on its way to the comet. As is often the case with missions to the outer solar system, it needed some gravity assist to get that far out. It had a flyby of Earth in 2005, and then a flyby of Mars in 2007. This Mars flyby was pretty risky. It would be just 250 kilometers above Mars's surface. Also during this flyby, which lasted 15 minutes, it would be completely in Mars's shadow. And because the craft is solar powered, the craft had to go into standby mode or its power levels would have been dangerously low. Meaning it relied on batteries that weren't designed for this task to keep the craft powered in order to switch itself back on after the flyby. It also meant nothing could be transmitted back to Earth as this was happening. So, full of jagged edges and sharp sides, cliffs, valleys and crevices. It's a breathtaking sight to behold, and is really a lot more interesting looking than anyone had previously thought. But upon seeing these images, mission planners collectively thought, how are we gonna land on this? You see, the Rosetta, if you were standing on its surface, you could probably jump off it altogether. Its gravity too weak to pull you back. There was eager anticipation and nervousness at mission control as Philae descended, as due to all the many different factors, there was a second, meaning that it only rose 1 kilometer from the surface before eventually coming back down again. Over the course of... I think most of us know what the planets look like in the visible light spectrum. Saturn's pale golden color, Jupiter's red bands and colorful clouds, and Neptune's dark blue hue. However, light is emitted or reflected by planets in wavelengths beyond our eyes' capabilities, like infrareds and ultraviolets, and often what we can see in these wavelengths is actually far more valuable to scientists than simply how a planet would appear to the natural eye. That's because certain things that are invisible to our eyes might be very visible in infrared or ultraviolet, or vice versa. And if we want to know what substances are found on a planet, the electromagnetic spectrum can help us again. In Jupiter's atmosphere isn't completely understood, but it's believed to be caused by the upwelling of compounds that originated deep within Jupiter suddenly becoming exposed to the UV radiation from the Sun. As they lift up to the highest altitudes in Jupiter's atmosphere, perhaps the most striking is to observe Jupiter using the 4.68 micron wavelength, as this shows the heat of the planet. Very interestingly, in this view taken by the Gemini Observatory, it is the lower altitude reddish bands that are the brightest. You see, Jupiter actually emits more heat than it receives from the Sun. It is contracting in size, which heats it up. This heat eventually makes its way out of the planet through the cloud deck. The heat escapes easiest where the cloud deck is thinnest, which is why features like the Great Red Spot and the white